Hello, everybody. Good morning, afternoon, or evening, depending on where you are. It's a great pleasure to welcome you to this webinar organized by the Copernicus Climate Change Service Program Energy Operational Service. So this is a service that is running operationally and is now come to the end of its second year. So we got a lot of interesting results to share with you, and so I'll pass over very soon to our great speakers for this webinar. Before doing that, I would like to just introduce a bit the service, the Energy Operational Service, but also myself. So my name is Alberto Trocli. I'm the director of the World Energy and Meteorology Council and a visiting professor at the University of East Anglia. And I've been leading this operational service. So we have been focusing on developing a service, operational service, which is not providing solutions, but is providing the tools for people to develop their solutions. But we have done this in such a way that we have interacted a lot with energy industry, and so the we have quite a strong interaction with various energy. Sorry, if I can ask, someone is typing on the background, please, if you can mute yourself. And so the the several variables that have been developed both for the climate, I'll show in a minute, and the energy. But the important thing is that this is something that is being done in close collaboration with the energy industry, as I said. And proof of that is that one of the partners is EDF, a strong contributor to the project and service. The project was led by the World Energy Meteorology Council with partners from France, CEA, Meteor France, Armin, and from the UK, Met Office, in addition to EDF, which I just mentioned, as you can see at the bottom of the slide. This is just the service in a nutshell. I just briefly present it. There's obviously a lot to be said about this, but in terms of expanding on it, but we just want to give you a brief overview about this. And we basically have three streams. One is looking at the past record from 1979 and to present, which is based on reanalysis. So the reproduction of climate, and as best as we can. This is just one, is the European ERA 5 reanalysis. Then we have the so-called present, which is really looking at the near future, 6 months in advance through seasonal forecast. And the third stream is climate projections. And for all the three streams, we have both climate indicators and energy indicators. For climate, we have temperature, wind speed, precipitation, solar radiation, and mean sea level pressure, plus a few others as well. But the main ones are this. And for the energy, we have electricity demand, wind power production, both onshore and offshore, solar photovoltaic, and hydro production, both onshore and offshore. And you will learn much more about this energy indicators in a minute through the presentations here. So we have developed all the data. We've got a very rich data set now. We are also planning to make this available through, aside from the climate data store, which is the place where you go get the data from the C3S. We also are going to make it available through a display or demonstrator. So this is being developed as we speak, but at the moment you can still refer back to the previous two demonstrators that were built with previous project. On the left here, you got ESM at the top with the link there. You will have all the presentations, by the way, so don't need to rush and write down what you see, but it will take a few days, but you eventually will have the presentations and also the recording, in fact. And the And then the bottom one is the Clean for Energy project that produced another demonstrator, and they are converging into one, which, as I said, is being developed. For the webinar now, we have 3 great speakers. One speaker is going to talk about the validation of the C3S energy historical capacity factors, so everything to do with the energy indicators. And then we're going to also look at how these indicators are used for a case. It's not really a case study, but it's showing how these indicators can be used for a season, a particular one, winter 2019 and 2020. So we're going to see how those indicators behaved during the past winter. We'll have also time for questions at the end, and you'll be able to type them at the end, but please feel free to type them on the question tab anytime. We're going to collect them and then address them at the end. So without much further ado, I would like to now pass over the baton or presentation or floor to the first speaker, who is Dr. Yves-Marie Sandrinan. And Yves-Marie obtained a PhD degree in 2016 at the University of Kassel, Germany, on the modeling of regional PV power generation for meteorological data. And he was successfully researched at CEA, France, ISET, Germany, Fraunhofer in Germany, and since February 2017 at MinParisTech in the south of France. He is currently responsible for activities on solar resource assessment at MinParisTech. And Yves-Marie has also led numerous projects linking meteorology, renewable energies, and their integration into energy supply. So it's a pleasure to have Yves-Marie now present the validation of the energy indicators for C3S energy. So over to you, Yves-Marie. Thank you.
Thank you very much, Alberto. So let me first share my screen. Can you see my screen? Yeah.
Yes, but if you could make it full screen, please.
Yeah. Okay. So in this presentation, I would like to show you some preliminary results of the validation of the energy capacity factor. But before, let me remind you the context of this.
Yves-Marie, sorry.
Yeah.
Have you moved away from the microphone?
Can you hear me?
A faint. Can you try again? Okay, this is better. Yeah. Thanks.
It is better. Okay, thank you, Alberto. Yeah, as I said, let me remind you the context of this work first. So as Alberto introduced, we did this work in the context of C3S energy, and the objective of this work is to translate some climate variables in energy indicators. And this translation has been made for different energy resources, namely the electricity demand, wind power production, photovoltaic production, and hydro production. And this is also been done for different climatic data. That said, this means that our energy conversion models has been applied to different kinds of input climatic data covering period from 1979 to 100 with different time resolution, different spatial resolution, different characteristics. And our energy conversion model has to be applied in any location in Europe, even if no specific information is available. So this means that we have to select energy models that are really versatile or flexible so that we can use them anywhere for different climate data set. And this flexibility has been favored over accuracy. So this is a very important notion to have in mind in this validation process. So we won't look at best possible model, but given these constraints, we now want to verify that the output of our model is plausible. For the validation, we needed some reference data, and we decided to use data from ENSOE, the European Network of Transmission System Operator of Electricity. And yeah, ENSOE did a really great job by collecting input from different transmission system operator in Europe, which saved us a lot of work. So it is really a great input data set. But we have some issue with the data due to the different input and different mechanism of the different TSO. We have difference in the data between the different countries. So the data availability is different from one country to other country. We have some mismatch sometimes between the given install capacity and the generation data. It can also happen that the data change with time, or that we have some change of a characteristic of the data with the time. I will show that afterwards, some example. But the good news is that we have good contact with TSO, and we have some active exchange with ENSOE staff, so that we are looking for solution to handle this problem. So let me start now with one of the biggest issue we had in this validation work, and it is the problem of the install capacity. Because in the ENSOE data, we have time series of power production, but to have the possibility to reproduce this power data, we need some information about the installed capacity. And to illustrate the issue related to the installed capacity, we represented the time evolution of the installed capacity of solar and wind in France in this example. So I don't want to go into the details of the different data sets, but we show this evolution for different data sets: ENSOE, Eurostat, IRENA, and RTE, which is a French national transmission system operator. And you can see that there is non-negligible difference with among the different data sets. And this is an unavoidable source of uncertainty, which makes the validation difficult. So now I would like to start with energy demand and start with one example, Austria. The red curve on the left plot is taken from ENSOE data. And you see that there is an obvious change of characteristic of this data set during the period. In 2010, the mean of the demand spring in one time. And this is due to a change of the perimeter to the perimeter of the demand. So it's not an error. It's just something you have to understand when you handle the data. So just that to say that it's really important to understand what is behind this data to handle them properly. Pragmatically, we sorted out such events. In that particular case, we only considered data after 2010 to get rid of these effects. And this is my transition to the modeling work, because in this particular case, we use data between 2010 and 2015 to model the energy demand using a machine learning model. In that particular case, it's a GAM model, and the validation has been done between 2015 and now. And you can see on the right plot the result of the validation. And for demand, we have really good match between model output and reference data from ENSOE, as you can see in this scatter plot on the right panel of the figure. Yeah, this work has been done for all countries in Europe, and generally the results are pretty good, at the exception of some countries, of course, for example, Luxembourg or Lithuania. So we had a look at this country, and okay, we are looking in more detail. We are making a more exhaustive validation, but we we believe that there is some issue with the data that explain this greater value of the noise in the validation. So now I would like to go to the hydropower. So for hydropower, there has been more intensive work. Different statistical models have been tried. So all these models are using random forest, but with different features. So air temperature, precipitation and snow depths have been considered, and we benchmarked different models and selected the most simple model with the best results, which is the one represented by the green bar in this performance analysis. Okay, and it's also important to mention that we differentiated the reservoir hydropower and the runoff river hydropower, of course. For these two hydropower technology, we use the same model, which is a random forest model using lagged air temperature and precipitation, which gives really good results, as you can see it on the left panel. So the scatter plot of the model output against reference are displayed for all countries, and for the reservoir in the upper panel and for the runoff river on the lower panel. In blue, you can see a concurring model, which shows much more dispersion. So you see that we obtain really an added value by making this model comparison, and the resulting data are really satisfying. This work is, by the way, documented in a publication that you can find on the we can disseminate the link later. For wind power, we did a similar job, but we had there more issue with the installed capacity. So we decided to represent the capacity factor as a function of the power data. So just as a reminder, the capacity factor is equal to the power normalized by the installed capacity, and this is what our model it is a direct output of our model. So we directly compare output model with the power data from ENSOE, and to take into account the installed capacity, we represented here with different colors. Yeah. And you can see the effect of the evolution of the installed capacity. It is really observable for France or Germany or Denmark. So you can see that the slope of the scatter plot decreases with the installed capacity, which is normal. You have some strange issue happening for the Netherlands. So there is some obvious issue in the ENSOE data again. We have two countries with under average results, which are Austria and Switzerland. And we looked at the data to understand these results, and yeah, the explanation is quite simple. We assume an homogeneous distribution of the installed capacity of a country. So we considered all locations in a given country, but in Austria and Switzerland, we have the Alps with really specific meteorological consideration, and in the next version of the model, we have to filter out location in the Alpine region to improve the model. So this is something we know, but this is, as I said, preliminary validation, which is also aimed at identifying such issue. So what we can see is also for Slovenia, a lot of noise. As I will show you that later, it is due to another reason, and this reason is that for country with very little installed capacity or very little wind farms, then our model is not performing that well, because we had to make some assumption on the characteristic of the plants in a country, and this assumption increasingly good when the installed capacity is increased. So, and to illustrate that, we displayed the spatial distribution of the error metric in this map. And we decided to concentrate on the correlation coefficient. Why? Because the correlation coefficient is more robust to the issue with the installed capacity. Not 100%, but more robust than other error metrics. And this confirms what I said earlier. More specifically, where some issue for Switzerland and Austria due to the Alpine region. We have also issue with Slovenia, and the reason for Slovenia was that there is a very little installed capacity. To show that, we plotted the correlation coefficient, so the selected error metric as a function of the installed capacity for the different country in 2019. And you can see indeed that Slovenia has the lowest installed capacity. And it is expectable that the performance is quite well. You see this line. So the result for Italy is quite poor, and we are looking for the reason currently, so I won't go into detail. But what we can see is that the most part of Europe, we have quite satisfying results with correlation coefficient above 0.8, which is really satisfying. And it is in any case a validation of the plausibility of the output of our model. So enough for wind. Let me go to the PV part. We did exactly the same kind of analysis for the photovoltaic energy. Here again, we have a matrix of scatter plots showing the capacity factor calculated with our models and ERA5 against the ENSO-E power data for the different country. Here again, you can see wonderful the effect of the installed capacity on the scatter plot. So namely, the slope of the scatter plot decrease with increasing installed capacity. This is obvious for Denmark, France, the Netherlands. Like for wind, we have a high dispersion of the scatter point for Austria and Switzerland, and we believe this is due to the same reason to the effect of the Alpine region on the aggregation. So we have to make this fix. Yeah, Spain is also a problem. We have some problem, and the reason is that we have not only PV power generation in the solar time series of ENSO-E for Spain, while we are only modeling photovoltaic energy in our energy model. So the presence of, yeah, for Spain, we have also CSP power generation. So taking this into consideration, it is obvious that we cannot have good results because we don't consider CSP. So this is also something to consider in the future. The point dispersion is quite high also for the UK, but you can see that with the time the correlation is increasing. So this is something also to consider. But yeah. And for Slovenia, again, the results are quite average, I would say. But for all other countries, we see that the scatter plots are quite nice. We have a good correlation between model output and ENSO-E data. And to understand the difference between countries, again, we represented the distribution of the correlation coefficient on the map. And here the results are much better than for wind. We still see under average performance for Switzerland, which is due to the presence of the Alpine region. It's not that obvious for Austria, but we see on the scatter plot that it is still an issue, and for Slovenia as well. But well, generally for photovoltaic energy, the results are really satisfying. at the exception of Switzerland, all models have a correlation coefficient greater than 0.88, which is really satisfying, and it is in any case validating the plausibility of our data set. And now I would like to give a few concluding words. Once again, just to put things into perspective, the objective of the C3S energy dataset was to make a database of plausible data, but that can be found for any location in Europe and for different climatic data. So our focus is laid on the flexibility on the model, less than on the accuracy. But we want in this validation work check the plausibility of the data. And this plausibility has been, in most cases, validated by this work. It should, however, be mentioned that this validation has been hindered by the uncertainty on the reference data. On the one hand, for some country, for the power data from ENSOE, and for almost all country by the uncertainty on the installed capacity. We found out some potential improvement that can lead to an improvement of our energy model. So that's also good news. So the data are plausible, but they can be even better. One obvious example is only considering regions that are not in the Alps would already bring out an improvement. And yeah, these results are only a preliminary results. In parallel, we are conducting a systematic validation of all the energy model, and this result will be detailed in the publication very soon. And in parallel to that, an intercomparison of different data set is under progress in cooperation with the Joint Research Center in Petten. And this intercomparison includes not only C3S energy data, but also renewable energy data, the data from MRS and other data set. So these are my last words. If you have any question, I would be really happy to answer them.
Excellent. Thank you very much, Marie. Very informative assessment of all the indicators, and also very promising and satisfactory results, as you said. We are already receiving some questions, so please continue to type them in, and we'll, as we said, we'll address them at the end. We're now going to move to the second presentation, which is a two-person act. So there is Christian is going to present the basis of the seasonal energy indicators, and then Luca is going to tell us about the focus on winter, as I understand. So I just introduce, let me introduce Christian Viel. So Christian has a background in meteorology and several professional experiences as a weather forecaster, hydrology forecaster, weather product developer, and he has joined the Directorate of Climate Services of Meteo France in 2012. He's been working both in operational production of seasonal forecast outlooks and in climate services development. He actively supports regional climate fora like in Europe, like MEDCOF and CECOF, and he has been involved in several European projects related to climate services at seasonal timescale, like Euporius, C3S project, this one, and others, Medscope, ProSnow, and Seclifern. So it's a pleasure to have a presentation from Christian now. Over to you, Christian. And then we'll halfway through, we'll then introduce also Luca.
Okay, thank you, Alberto. So do you see my screen?
Yes, if you can make it big. Yep, very good, thank you.
Okay, thank you. So now the focus of this presentation is more about seasonal forecast. So with Luca, we will show you what happened during last winter, and the capacity of seasonal forecast to anticipate the last winter situation. So there will be two parts in our presentation. First, I will give you an overview of last winter through climate variables. And then Luca will focus on energy indicators from the project. So what happened this winter in terms of climate variables? Here you can see a summary of the winter circulation with the mean sea level pressure anomaly map. This is a mean anomaly covering the 3 months of the winter, DGF. And as you can see, there was a north-south gradient between negative anomaly in the north part of the domain and positive anomalies in the south. So this is typical of a positive phase of the NAO, the North Atlantic Oscillation. And as a consequence, there were stronger westerly or southwesterly flows over northern Europe. So more strong wind events, of course, than usual in this part of Europe. And globally, a mild air advection from the ocean over the whole continent. And other consequences in terms of precipitation and insolation, for example. Here I've noticed the more wetter, the wetter or more windy condition or less insolation in the northern part, and the opposite in the south part of Europe.
Christian? Hello, Christian? We lost our speaker. Sorry, we're trying to fix the issue. I think, okay, it's coming back. It probably had a dip in the... Okay, sorry, Christian, we lost you for a little while.
Okay, so I come back maybe to this slide.
Yeah, it's, yeah, the third one after the NAO plus, yeah.
Okay. Okay, so just a quick come back to this slide. This is a summary of the situation with this NAO plus pattern and its typical consequences in terms of westerly flow, so stronger westerly flow than usual in over Europe, especially over northern Europe, and so more strong wind events than usual in the northern part of Europe, and also a milder advection over the whole continent, and some other consequences in terms of precipitation or insolation. Here you can see these consequences for 3 parameters: temperature, precipitation, and global radiation. And you can see this north-south gradient for precipitation, for insolation, and globally this warm anomaly over the whole continent for temperature. So the question now is, how was it predicted by seasonal forecast models? So on the left side, you can see the C3S multimodal forecast issued in November, so available in mid-November on the Copernicus website. And this is a forecast for DGF, the mean forecast for DGF. And on the right side, you can see what effectively happened. So I've chosen three parameters. First, mean sea level pressure, and you can see that this is a very good forecast of the dipole of anomaly pattern, with the same pattern as I described before. And for temperature, the warm anomaly was correctly forecasted by C3S. And for precipitation, also a forecast of more precipitation than usual in the north part of Europe, and less precipitation in the southern part and the Mediterranean basin globally. So globally, the forecast over Europe was successful. But beyond this verification, a legitimate question is, was it predictable? So in other words, could we say in November that we trusted in this seasonal forecast? So to answer this question, what climatologists generally do is looking at four things from the tropics. This is a major source of predictability at seasonal scale, even at our latitudes. So first, let's go back to October, and we can look at the SST anomaly map in the upper part of this slide. And the first candidate of tropical forcing is ENSO. And for this situation, you can see that there was no clear anomaly in the Pacific, in the tropics. So there was no El Nino or La Nina event. So this is what we call a neutral ENSO situation. But over the Indian Ocean, there was a very strong east-west dipole in sea surface temperature. And it had been there for a few months, and its intensity was very high. This was what we call a positive IOD situation, Indian Ocean dipole situation. And this kind of situation, in this kind of situation, there are strong modification of large-scale convection in the area. This globally the same mechanism as ENSO. And it leads to local consequences in terms of precipitation, for example. So you remember the persistent drought and the fires in Australia, for example. This is typical of this consequences of this Indian Ocean dipole. But it can also induce modification of circulation at distance through what we call teleconnections. This is what the Copernicus models suggested in this situation in the November forecast. And there are some impacts up to Asia and Eastern Mediterranean. So we have, for this situation, identified some strong oceanic forcing from the Indian Ocean and teleconnection up to the Mediterranean basin. So this kind of elements could lead to a better predictability globally of the system. And another fact is that we had a good consistency between models in terms of circulation, for example, but not only. So, for example, here you have the mean sea level pressure of 5 of the C3S models. And globally, even if there are some differences between models, the idea of the NAO+ circulation was forecasted by a majority of the models. So, as a conclusion, there was a good confidence in this forecast, and the forecast globally was good. So this is something interesting for this situation. Of course, we know that for Europe, the predictability is globally poor. If we look at scores over the MCAST, we calculate scores, we see that we don't have a big added value compared to climatology. But there are some opportunities, some windows of opportunities for seasonal forecast, when we have specific conditions and we can identify sometimes this kind of conditions, and seasonal forecast can be, of course, much more useful in this kind of situation. Now, I leave the floor to Luca.
Okay, thank you very much, Christian. We're going to now switch to a presentation from Luca. And Luca is a meteorologist at Meteor France, and is part of the energy team, and he's made very strong contributions to the C3S energy operational system service. Over to you, Luca. Thank you.
Hello, I hope you can hear me well. So I will carry on with a focus on energy indicators. So as you know, we are producing 4 energy indicators: onshore, offshore wind power, electricity demand, hydropower, and solar PV power. And we do so with 3 seasonal models that are ECMWF-SYS5, Météo France System 7, and METOFIS GLOSSY 5. Before showing the figure, this is bias corrected data. Bias corrected via content mapping. That is basically, it makes seasonal forecast distribution to fit the reference error 5 distribution. There is more detail on our models and on the bias adjustment in the last webinar that we did back in February. So if you want to have more detail, it is available on YouTube or on the WAMC website. So let's go for 10-meter wind speed. As Christian said, the climate variables were well foreseen this winter. So for climate, only wind. So there is a general agreement on a stronger wind anomaly on the northwestern part of Europe, and a weaker wind offshore Portugal. This is 3 months averages, typically the relevant time scale for seasonal signal. And the initialization is November 2019 and going on for December, January, February of this last winter. So although for the rest of the presentation, the reference will be error 5, and that we assimilated to observation. So now let's look at the observation. So you can see that the pattern there are really similar, and this is also interesting because there is no major discordances. There is many parts of where the models don't see any signal, but when there is a signal, it is quite the correct one. I want to emphasize also that the most important there is the sign of the anomaly. Not maybe the amplitude, but the sign. So let's continue with offshore wind power. So offshore wind power is built from 10-meter wind speed extrapolated to 100-meter wind, on which a 8-megawatt wind turbine power curve is applied. So there is a general agreement on negative anomaly on the northwestern parts of the domain, so a broad Atlantic domain, and a positive anomaly on the Mediterranean basin. It may be surprising because in the last slides, the wind was expected to be stronger on the northwestern parts. So maybe it is due to the fact that the wind are too strong and the power curve and the wind turbine would stop. With the reanalysis in the energy model, the patterns are quite similar. So this is really interesting. And you can see also that the wind in the Gulf of Lion was well predicted by the 3 model. So this is really interesting. For onshore wind power, it is the same kind of transfer function, but the power curve is a typical 345 megawatt wind turbine power curve that is commonly used onshore. So model were expected a lower production around UK and on the contrary a better production around Austria to Hungary and also on Scandinavia. When you can see the observation, you can see that it is quite well reproduced. There may be some little spots of differences, maybe on Poland, but yeah. But the forecast is also quite well. So for solar PV model, solar PV model for seasonal takes 2 meter temperature and global horizontal irradiance as input. And the output is a daily mean capacity factor. So this is a very experimental. So the most interesting here is the sign of the anomaly again. So as you can see, the forecasts are less good, but still it is interesting that the most important anomalies around from Italy to Greece and at the top of Scandinavia are well reproduced. But you can see here also major difference, major mistakes on Spain. But the pattern is still really interesting here. So for electricity demand, the indicator is available only country aggregated. So I display here the monthly mean of the indicator. So this is the initialization of November running on December to February. So in red the forecast and in blue the reanalysis era 5. So for example, on the left bottom corner for Meteo France System 7, you can see that the model is behaving. It was my phone. I'm sorry for that. It is interesting that the model are quite different, and Mary told us about the differences of the INSOI data and the model calibration and validation in the different countries. So you can see that for France, where we have good quality INSOI data and many grid points of our model, we have a quite good model, even for Germany. But for example, for Czech Republic, it is not as well. But this is quite interesting although because you can see that the variation are quite okay, and there is some months for this January where the points are really close. So this is interesting. Before concluding, just a quick recall of what are usually the skill of our seasonal model. And so I display here the anomaly coefficient correlation. That is a skill score that evaluates the capacity of a model to reproduce the interannual variability. So 1 would be perfect correlation, and -1 would be a perfect anti-correlation, and 0, no skill. So as you can see, usually on the 24-year hindcast period, so 1993 to 2016, you can see that, for example, the SPV and the SPV is quite wrong and bad on France or the Greece island, Poland and UK. And although you can see that the skills are usually low on the Mediterranean basin for offshore, or low on the central part of Europe for onshore. So when you see the good forecast of this last winter, actually this is a quite satisfying predictability. This last winter was really okay. And we hope that with more knowledge on the links and the teleconnection between tropical to mid-latitude, we hope that the forecast will be better and better. I will skip this diapo. So to conclude, we are happy that this winter was well predicted. And now we would like to do some verification, maybe operational, like the really observed solar production on Europe, or the wind power production onshore, offshore, for example, in North Sea, where we could examine and determine if actually the wind turbine stopped due to too strong gust or wind. Now, user, it is in your hands actually, because the data is fully available online. We are waiting for feedbacks. We are ready to answer the question. So feel free to contact us, and I really hope to see you at the workshop that is in 2 weeks. Thank you very much.
Okay, excellent. Thank you very much, Luca. And this was a great way to apply the data we produced so far under the C3S energy. I should like to emphasize, though, that the data, Luca referred to the data available online, but unfortunately these are not available yet. They are in the process of being published online through the climate data store I mentioned before. But now we have some minutes for questions that you put in there, and please feel free to continue adding questions. So I'm going to show the questions here, and I'm going to address them as quickly as we can. We may go a bit over the hour. Those who like to stay, please stay with us, and we'll address as many questions as we can. And the first one is whether WMC has data for small island developing states as well. So yeah, we, as people have noticed, we have discussed only Europe, because that's what we've been producing. The data is not owned by WMC, I should say. It's all data from C3S. So this is all products that belong to C3S. We are supporting C3S in their work. And but in terms of small island, depends what data is available. There are climate data available through the reanalysis and seasonal forecast, and we are also looking to make available energy indicators in the future for other sides of the world. But please also send some requests, a specific request that we cannot satisfy everybody, but that we are collecting all the requests so we can make a case for the important areas that we want to focus in the future. So moving to the other questions. So thanks, Anna, for the question. And Roberta asked a question for Yves-Marie. And I can read it quickly. Yves-Marie, if you want to get ready to answer this, please. When you consider weather data from ERA 5, from ECNWF, what are the variables you consider for wind? 100 meter or 10 meter U and V components, and then you calculate the speed. And what about solar radiation, surface net solar radiation, GHI for solar thermal, and total sky direct solar radiation at surface, clear sky for PV. Many thanks. From Roberta.
Yeah, thank you, Alberto. Thank you, Roberta, for this question. So I'm answering the first question related to wind. Laurent Dubu made the calculation from RT. So Laurent, if I say something wrong, please interrupt me. The wind speed has been taken at 100 meter using UV components. The wind speed velocity has been calculated and then vertically interpolated at up high, and then reference power curve, a single power curve, has been used to calculate the power value. So you see, we have a really robust approach for calculating the wind power. So what about solar radiation? So as you see, we only considered PV power generation, so no thermal power, and we use GHI and 2-meter temperature, the GHI and the calculated top of atmosphere radiation is enough to transpose the horizontally radiation on the plane of array, and then we can make the whole PV power calculation this way. So I hope this answers your question, but feel free to send us a mail if this answer is not enough. Thank you. And I go to the next question. So
yes,
thank
please.
you for the nice thoughts regarding PV. Where did you get the reference data? Does it include system of all sizes and even those smaller than 1.5 kilowatt peak? More difficult to trace, Sarah Freitas. So thank you, Sarah. That's a very good question. I would invite you to see the webinar we made 1 year ago in May 2019, where we presented the PV model. It is indeed tricky to take into consideration small PV systems. What we did is that we use a sample of small systems based on, I think it's a 100,000 PV system in Germany, and we try to understand the characteristics of these PV systems and to generalize this characteristic to other countries using the latitude and some geographical information. And this way, we hope to address we hope to address this issue of small PV system, which remains a tricky issue, I would say.
Okay, thank you very much, Yves-Marie. And if we now move to the other, sorry, I'm going to show the next question. I think it's more for Laurent. If Laurent, you want to address this about the load for demand. So sorry, Laurent Dubu was not a speaker, but he's been working one of the main contributors of this operational service. So Laurent Dubu from RTE, before he was at EDF. So some of you would know him. Please, Laurent.
Yeah, can you hear me?
Yes, yeah, thanks.
Yeah, okay, good morning, everyone. Yeah, I'm not sure I fully understand the question, but my understanding is that you have only 30 data for annual demand, and you want to make long-term prospective studies. I guess this is correct. And then in that case, it's, I think, very difficult to make a forecast of what the demand would be. But what I would suggest in that case is to try to determine a link between the demand at annual time scale and climate parameters, mainly temperature, for instance, and then try to make some kind of basic extrapolation into the future based on the evolution of temperature. So very, very simple ratio between temperature and demand or something like that. But I'm not sure I really understand your question, and I suggest that you send me an email. You can ask Alberto, or I will send me yours, and I will contact you to go deeper into the answer.
Okay, thank you, Laurent. And then the next question about the correlation coefficient of installed capacity. You also calculate the correlation coefficients of your weather data, question mark, with the weather station observation data. So from Wenshun. So that's for Yves-Marie, I think.
Yeah, I think I can answer, and maybe the question holds also for the seasonal forecast. I start with my part. In the C3S energy, we didn't look at the correlation coefficient of the data with weather data, but we do that in a parallel activity, namely in the last publication of MinParisTech using the Pirata data on the Atlantic Ocean. So this is done, of course. We are interested also into the input data, but in parallel to this activity.
Okay, thank you. And I don't know whether also, but, well, the next question is for either Christian or Luca. How are anomalies defined, and what is the reference?
Yeah, the anomalies are defined in comparison to a reference period that ranges from 1993 to 2016. So we do a climatology of the climate variable, and we take the bias adjusted and we determine the anomaly, and also its position, its ranks to have the percentile, sorry, the percentile. Although maybe I can address the precedent question. Yeah, we did the anomaly coefficient correlation for our weather data too. That was the slide that I did not show. Yeah, that's
okay. So maybe while you are speaking, if I can ask you to answer quickly also the last question from Prashant, the second question. During the forecasting, have you considered the seasonality also?
I'm sorry, the seasonality.
Okay, maybe I can, sorry? Maybe I can answer that. I mean, it's when we do the forecast, it's all considering past season, the same season. So the issue of seasonality is not so critical because we only consider specific season. There's no annual cycle, if you.
Yeah, and when to build the climatology, we consider the value around a kind of climatic window. So to determine and to make the bias adjustment, we take the value around plus and minus 15 days, so 31 climatic value to have a more robust climatology period.
Okay, and thank you, Luca. I think we are now getting close to the end, so I'll answer quickly number 7, which we already answered basically, but the seasonal forecast of energy variables are going to be available through the CDS, so the climate data store of the C3S. C3S again stands for the Copernicus Climate Change Service. Okay, and the last one, what is the ratio of installed capacity and generated energy? Well, that's basically the definition of the capacity factor, or 1 over capacity factor. So that's what, unless Laurent or Yves-Marie want to add anything quickly on this,
very short.
Yes.
So the variable of interest in the energy modeling is a capacity factor, which is also called the normalized power. It is basically what you mean. It is a ratio of the power in megawatt by the installed capacity. So it is really what we handled in this modeling work. If you have more questions, we can also maybe Alberto disseminate several publications where more information is provided on the modeling approach and the quantity of interest.
Yes,
recommend looking at that.
Yeah, and just to conclude on that point, the capacity factor is used because we want to focus on the variability of the signal and particularly what is coming from the climate as a signal. So that allows us to eliminate other issues to do with the knowing exactly how much power is produced at any one point. Okay, so just to conclude, that we are a bit over, but thanks for those that have stayed. We still have many people on the line, hopefully following what we say. So just to tell you about where to get the data, as we said, that we are building a new interface demonstrator. In the meantime, I mentioned the previous 2 demonstrators, but we also have another option here. It's built for educational purposes, but it also contains the same data as the ESEM demonstrator. So another way to get the data from. So here is the link underneath. So C3S, this is also a C3S product, and it's called Education Demonstrator. Also, we mentioned during the talk a few times the previous webinars. Here is a list of all the webinars that have been given during the project, the 2-year project, the C3S Energy, and all of the recordings are available at the link below. And finally, I just want to invite you, Luca, as already mentioned, the symposium for the energy industry, which is happening on Tuesday, 19th of May. It's going to be for 4 hours with an hour break in between. And here is the time, 8 to 3:13 UTC. So 1 hour behind UK time for reference. And you can register on Eventbrite. We still have a few places, I believe. Or the short version of the link underneath. Sorry, that's what it is. Maybe you managed to grab it, but as I said, the recording and the presentations will be available online at the WEMC and C3S. This is the link for the C3S Energy Service webpage. Can go to the C3S and search for energy sector operational. So you get this link and you find also our contact details. So I would like to thank everybody for the participation. We had a very good attendance, and for the questions, all the speakers, and please follow us. And the activity, I should say, will continue. The operational service will continue over the next at least a year and a bit, and we're waiting for the next round of Copernicus Copernicus phase 2 to see what is going to happen also to the this service and to all the other climate services. So watch this space and please get in touch if you're interested. Thank you very much again for your attention, and goodbye.